So, is it audible? Yeah, good evening. Yeah. So, today we are going to discuss the partial differential equations, right? So, quasi-linear equation, one more model actually we can discuss, and then we can go to the homogeneous linear equations. So, in the quasi-linear equations, so in this actually, so any equation of the form P into small p plus Q into small q is equal to R, where P, Q, R are functions of x comma y comma z, right? Yeah. Just a minute. Fine. Okay. So in that actually note down one more. So for this kind of equations, the solutions are straight away dx by p is equal to dy by q is equal to dz by r. Now this is the auxiliary equation, and for this auxiliary equation, find out the solution. That's it. So this solution, finally, if you express in the form of phi of uv is equal to 0. So this is the final solution, right? This is the standard method for any kind of quasi-linear equation, and that is the basic differential equation in case of partial differential equations, which you can use for solving other complex level of differential equations also, right? Now, note down one more problem based on this understanding. Solve mz minus ny, mz minus ny into p plus nx minus lz, nx minus lz, nx minus lz q is equal to ly minus mx, ly minus mx. Yeah, ly minus mx. Can I solve this differential equation? So this is again a quasi-linear equation where this is a function of x comma y comma z, and this is a function of x comma y comma z. This is also a function of x comma y comma z. Now, if all these three are the function of x comma y comma z, then the auxiliary equation is going to be, so this is dx by mz minus ny is equal to dy by nx minus lz is equal to dz by ly minus mx. So this is the auxiliary equation. Now for this auxiliary equation, we have to identify the solution, right? So how do we solve this? How do we solve this? Any guess? Any guess how we can make use of this to solve? Here actually, straight away if you solve it, this is a little difficult, because here if you notice, if you want to equate these two and try to simplify it, there is an unknown variable z. Suppose if you take these two, there is an unknown variable x. So this way actually you cannot straight away solve the equation with the auxiliary equation, right? Now for this actually, the way we adopt is, so let us consider x dx plus y dy plus z dz, right? So this way if you consider it, right, so this is going to be how much? So this is equal to plus y dy plus z dz. This is going to be x times of mz minus ny plus y times of nx minus lz plus z times of ly minus mx. So these two are equivalent. So in any random ratio like this, so if this is the case, if you multiply the same thing top and bottom, top and bottom, top and bottom, and add it all the numerators together, so that is exactly equal to the addition of all the denominators. That's what we have done here. This is one of the important principles. I hope you are aware of it. So this actually, I proved this principle earlier actually when I dealt with the integrations. Got it? Understood? Now this way, if you try to simplify this, this is going to be x dx plus y dy plus z dz. Now in the denominator, this is mxz minus myz, nyx plus ynx minus nlz plus zly minus mxz. Now this mxz will cancel out, and nyx will cancel out, lnz and zly, right? ynx just a minute, is the problem statement correct? Mz minus ny, nx minus lz, ly minus nx. Yeah. So this is L, this is not L. Yeah, now it's correct. Yeah. So this is Lyz. So these two will cancel out, and then all the sum together is coming out to be x dx plus y dy plus z dz divided by 0. So this is one of the important method. So you have to identify this form as 0. So for that actually you can identify appropriate values where you can multiply and make the denominator to 0. Then if you equate to any of this one, this is dz by ly plus mx, then if you equate to this, so this 0 getting multiplied here will come out to be a simple equation, x dx plus y dy plus z dz is equal to 0. Now if you integrate on either sides, this is going to be x square plus y square plus z square is equal to some random constant c1. Got it? Understood? So this is a method. Now actually this is one of the arbitrary function what we have identified. Yeah. Now actually from this, so can you identify one more such kind of ratio where you can make the denominator 0? The standard methodology to solve any kind of quasi-linear equations is try to equate 2 and these two together and relate the arbitrary constant with an arbitrary function. So that is the standard solution. Now actually we have got one arbitrary function here or one arbitrary constant here. Now exactly in the similar manner, if you solve for one more, that is L dx plus n dy plus m dz. So now take this ratio, then this is going to be L dx. So L times of mz minus ny plus, make it this m and this is n. So this is m times of nx minus lz plus n times of ly minus mx. Now if you simplify this also, L dx plus m dy plus n dz. So this is going to be lmz here and then lmz here, nyl. So NYL. So NYL here. And similarly, this part is getting cancelled here. So entirely it is coming out to be 0. Now if this is the case, then obviously LDX plus MDY plus NDZ equal to 0. Now integrate on either side, then Lx plus My plus Nz is equal to some random constant C2. So the final solution is going to be phi of Lx plus My plus Nz, comma, x square plus y square plus z square equal to 0. So this is the solution where phi is an arbitrary function. Got it? Understood? Any questions on this? This is one such kind of method where you can solve the differential equation by manipulating the coefficients. So when there is no possibility of solving these two together or these two together. What is phi? Phi is an arbitrary function. So this is a random arbitrary function. So when we discuss formation of the partial differential equations, I explained when there is an arbitrary function, how we can eliminate this arbitrary function to form a differential equation. Now when we solve the differential equation, the arbitrary functions will come out. So that will be decided based on the initial conditions. So this is arbitrary function. Got it? It's like arbitrary constant for us. How phi of c? So this is the solution, as I told you, right? I have not given the proof for you. So the proof is, if you want to solve any function like this, which is a quasi-linear equation, for that, so this is the auxiliary equation, and this auxiliary equation, if you solve it, and you are going to arrive at two different arbitrary constants, those arbitrary constants, if you put it in a random function, so that is equated to 0, will be the direct solution for this. So for that, actually, you have a complex level of proof. So that you don't need to understand. Got it? Understood, Deepak? Okay. Note down one more. Solve x into y square minus z square. Y square minus z square into p. Sorry, x into y square minus z square into q. This is, and then minus y into z square plus x square. I think there is a mistake in the textbook. So this is P only. This is Q. This is R equal to Z into x square plus y square. So can you solve this quasi-linear equation? So x into y square minus z square into P minus y into z square plus x square into Q is equal to z into x square plus y square. Can I solve this? So the auxiliary equation will be straight away, you can write dx by x into y square minus z square is equal to dy by minus y into z square plus x square equal to dz by z into x square plus y square. Can I solve this differential equation? Yeah, so you can multiply x dx plus y dy plus z dz. Now this is exactly equal to the same ratio. Now if we add these two together, this is x square into y square minus z square, and then minus y square into z square plus x square plus z square into x square plus y square. So this if you simplify it, x dx plus y dy plus z dz divided by, so this is x square y square minus x square z square minus y square z square minus x square z y square plus z square x square plus z square y square. Now z square y square and z square y square, x square z square and x square z square, x square y square and x square y square. So this is x dx plus y dy plus z dz, so divided by 0. So it implies this is going to be x dx plus y dy plus z dz equal to 0. Now if you integrate on either side, x square plus y square plus z square equal to constant. Got it? I think so. Other function x y z is equal to constant. Sorry, x z. I think so. This is x by y z equal to constant. Got it? So this one actually one arbitrary constant. Other function actually what you can do is multiply 1 by x into dx minus 1 by y into dy minus 1 by z into dz. You just multiply with this one. Then this is going to be simplified. Now if you multiply with 1 by x at the denominator, then this is y square minus z square. And then if you multiply with minus 1 by y with the denominator, this is going to be cancelled out. Then this is going to be plus z square plus x square, and then multiply with minus 1 by z. Then this is minus x square minus y square. Now z square will cancel, x square will cancel, y square will cancel. Then dx by x minus dy by y minus dz by z is equal to 0. Now if you integrate on either sides, log x minus log y minus log z equal to log c. So this is x by yz equal to some constant c2. So the final solution is phi of x square plus y square plus z square comma x by yz equal to 0. So this is the final solution for the quasi-linear equation. Got it? Got it? Any questions on this? Okay. So this is how you will be solving any kind of quasi-linear equations. So the methodology what we have adapted is, first write the auxiliary equation, and if you are straight away able to solve these auxiliary equations, then that is fine. But if you are not able to solve the auxiliary equation, try to manipulate the ratio so that you can get the denominator 0, and then try to integrate on either sides. You are going to get the solution for it. Then once we are done with quasi-linear equation, I will just introduce homogeneous linear equations of higher order. So homogeneous linear equations, right? Homogeneous linear equations. Now this is usually higher order only we will be discussing. Higher order. So in this actually the standard terminology, that's what we are going to adapt is, so small d, or sorry, capital D is usually represented for dou by dou x. And then d square is used for dou square by dou x square. And similarly, d dash is used for dou by dou y. And d dash square is used for dou square by dou y square. Similarly, the higher order, d cube is for dou cube by dou x cube, and d dash cube is for dou cube by dou y cube. So that is the terminology, that's what we are going to use in case of higher order differential equations. Now, we are discussing the higher order differential equations to a specific methodology of only the constant coefficients. Because if there are variable coefficients, the complexity involved is very, very high. That comes under the category of non-linear differential equations, which will be very tough to solve. Got it? But in our syllabus, we have only with constant coefficients. So that is, we are lucky enough. So this is, suppose if the differential equation is d square minus 2 into d dash plus 3 into d dash square is equal to of z is equal to f of x comma y. Now, this is one of the homogeneous linear equation. With constant coefficients. This is with constant coefficients. Now here if you notice, the power is 2 for all the terms in the equation. So this is the condition. Now here actually there are d and d dash product. Now it is coming out to be 2. And here d dash square. This is again 2. And this is 2. So this is 2. This is 1 plus 1. This is 2. So all are equal. So that's why we call this as homogeneous linear equation. Now these things has to be only the constant coefficients. So the constant coefficients. So this is the constant coefficients. So if there are any x or y are involved, then we say the variable coefficients. That is out of syllabus for us. Got it? And the right side part can be any function of x comma y comma z. Usually it is a function of x comma y. Now in this kind of case, the solution, the way we have to find out is, in case of normal ordinary differential equations, if it is a homogeneous equation, then for higher order equations actually we have some specific methodologies. That is, we find out the complementary function separately and the particular integral separately. Now exactly in the similar manner, even here also we have to find out the complementary function separately and the particular integral separately. Got it? So for finding out the complementary function, so solution, total solution is equal to complementary function plus particular integral. So complementary function and the particular integral will be the total solution for a homogeneous linear equation. Now the auxiliary function, complementary function we find out. So we have to write the auxiliary equation. We have to find out the auxiliary equation and then solve the auxiliary equation based on the roots write the solution or write the complementary function. Complementary function. So this is the methodology we adopt to find out the complementary function. And the particular integral, depending upon the function what we have it here, So there are different approaches to solve that particular integral separately. Got it? So note down this. So I will explain how to find out the complementary function for a partial differential equation in a standard method. First you note down this. Done? Okay. Then so we'll take one problem and based on that actually we'll solve it. Solve d cube minus 6d square d dash plus 11d d dash square minus 6d dash cube equal to 0. Now actually on the right side actually he has given simply 0. Now in this problem statement, so being it is 0 only on the right side, then there is no need to find out the particular integral for this because this is a 0 function. So we are left with only the complementary function. So in solving any kind of differential equation, whether it is an ordinary differential equation or a partial differential equation, so there are two parts usually we find out. So one is the complementary function and another is the particular integral. Now this is also called as the transient solution. And this is the steady state solution. So this steady state solution is dependent on only the right side function. Now if you take a simple harmonic motion, in the simple harmonic motion, the right side function if at all it is there, and this is what we call as the forced oscillations. Finally, this is the one which will govern the oscillations of the simple pendulum, right? But if it is 0, then we say the natural oscillations, where you just give the moment and then left it. So it keeps on goes this way, right? And then slowly it will come down to 0. So that behavior is exactly dependent only on the differential equation on the left side. But the right side part is dependent only for the forced oscillations. That means this will finally decide what should be the frequency this particular differential equation should have it. So that's why this has got utmost importance. This is only the transient behavior what we are going to solve it here. The steady state behavior will be dependent on the right side part. But for this particular case, what we are going to solve is only the transient solution because there is no forced input here. Got it? So now actually, so this differential equation, if we divide by d dash cube, then d by d dash whole cube minus 6d by d dash whole square plus 11 d by d dash minus 6 equal to 0. Got it? And then usually we keep d by d dash is equal to m, and then this is going to be m cube minus 6m square plus 11m minus 6 equal to 0. Yeah. So now actually this is the auxiliary equation. No, transients will keep on dying, right? So forced oscillations actually the final solution. That is, this will decide what should be the frequency of the oscillations. These are damped oscillations. Damped oscillations we mean we just give the display. Suppose if you take the simple pendulum, you just lift it like this and leave it. then actually after some time actually it will slowly come down and then actually finally come out to be 0. So that behavior is decided by this differential equation. Got it? It will die down because of the natural friction forces. But this will try to keep the same frequency depending upon the whatever the frequency what we are going to give it here. Got it? Got it or not? It is going to die down. This is only the transient behavior. Now this is, suppose if I keep m is equal to so what are the solutions of this? What are the solutions of this particular equation? So if I keep m is equal to 1, then this is going to be 1 minus 6 plus 11 minus 6 equal to 0. So m is equal to 1 is one solution. If I keep m is equal to 2, then it is going to be one more solution. That is, so 2 cube minus 6 into 2 square plus 11 into 2 minus 6. This is again coming out to be 0. And then m equal to 3. Again, 3 cube minus 6 into 3 square plus 11 into 3 minus 6. This is again come out to be 0. That means this can be written as m minus 1 into m minus 2 into m minus 3 equal to 0. So here m is nothing but d by d dash. Now these are, suppose if I take one root, m minus 1 equal to 0. Now m minus 1 equal to 0. M is nothing but d by d dash minus 1 equal to 0. Now this is ideally, this is a differential equation. D means I have just given the definition. D cube means dou cube by dou x cube. But this has to be operated on some function, right? That is usually whether it is mentioned or not, it is always treated as z. Now here, this is z here. Now this z value is nothing but dou, so dz minus d dash z equal to 0, or dou z by dou x minus dou z by dou y equal to 0. So this differential equation actually we should be solving it. Suppose if for any random value, let us say I call this value as, let us say m1. So suppose in general if I or d minus a. So this is a generic solution where d by d dash is equal to a. Now if you operate on this, then this is going to be 0. Then the differential equation is going to be p minus a cube equal to 0. So this is the differential equation for one particular factor. Got it? Understood or not? Now we have to solve the differential equation. This differential equation is one of the solutions for this entire differential equation. Similarly for this one, you have to solve each and every factor and then finally find out the solution. The sum of all the solutions will give the complementary function for this entire differential equation. Got it? You note down this, then I am going to solve this differential equation. Note it down. Okay. Then once you know this value, then I solve this a generic differential equation where m is a factor. Sorry, a is a factor for this. So p is, so the solution for p minus a cube equal to 0. Now this is a quasi-linear equation. So for this quasi-linear equation, this is dx by 1 is equal to dy by minus m minus a equal to dz by 0. So this is, if you take these two, then dx equal to dy by minus a, or dx plus dy by a equal to 0. So this is ax plus y equal to some constant c1. This is 1. If you take any other equation, then this is going to be, so if I take dx is equal to dz by 0, So this is dz is equal to 0 or z is equal to constant C2. So this can be expressed as z is equal to ax plus y. So some random function of. So this is the finite solution. Got it? Understood? This one. Similarly, if you take another factor, so m minus 1, m minus 2, m minus 3. Three different factors are there. Suppose this is a1, I call this as, another solution is z is equal to a2x plus y. So this is another function of. Similarly, z is equal to some xi of a3x plus y. So this is another solution. Now the complementary function is nothing but phi of a1x plus y plus psi of a2x plus y plus xi of a3x plus y. So this is the complementary function. Got it? Why we took phi and psi? So as I told you, so this is an arbitrary function which we will bring in. Now this is a third order differential equation. That means this differential equation we have got by eliminating three arbitrary functions. Those three arbitrary functions will come back if you solve this differential equation. That is these three. Got it? Understood? Okay. So this is how actually you will be solving the differential equation. Now here actually the roots are real and equal. The roots are real and equal. Sorry, real and unequal. So exactly in the similar manner you can solve if the roots are real and equal. Note it down. So this is as if like in the normal ordinary differential equation, the way we prove if the roots are real and equal, then the way we write it is, so there actually we write the arbitrary constants. Now we are writing the arbitrary function. That is the only difference. The rest of the thing is as it is. So the complementary function, this is equal to phi plus phi of a1 or ax plus y plus x times of psi of ax plus y. So this is if the roots are real and equal. Got it? So here there is one x extra comes as the roots are real and equal. Got it? So why we are doing that way is, suppose if I have, let us say d minus a or m minus a whole square is a factor. So if this is, the roots are real and equal in this case, right? If the roots are real and equal, then you can write this as m minus a into m minus a into z equal to 0. Now if this is the case, then the way we adopt is, this we treat this as some random function v, then m minus a times of v. So this is equal to 0. So this is, so m is nothing but dou v by dou z, so dou v by dou x minus a times of dou v by dou y equal to 0. So the arbitrary function, so this is the auxiliary function for which you can find out the v value. We just proved that is phi of ax plus y. This is the v value, right? Yeah, for three real roots it is going to be x square that comes. But this inside function will be same for all. Now actually that's what I am going to prove that. See this. So this is v is equal to phi of x comma y. Earlier actually this is z. Now actually this is v. So where the relation between v and z is m minus a times of z, you have treated as v. Now this one, if you solve it, this v is going to be m minus a times of z is equal to phi of ax plus y, where ideally some constant c1 is ax plus y, and then v is equal to constant. This is another second constant. Now, if you put this value, this is going to be dou z by dou x minus a into dou z by dou y is equal to phi of ax plus y. So this ax plus y is some constant. Now here, if you solve this one, dx by 1 is equal to dy by minus a is equal to dz by phi of some constant c1, where since c1 is equal to ax plus y. Now if you integrate these two, so this value, if you find out, this is, so ax plus y is equal to some constant c4, and then this, if you integrate, this is phi of a into x is equal to z. So this is z is equal to x into phi of ax plus y. So the sum of these two solutions, the final solution will be phi of ax plus y. So this is the final solution. So one with x, another with no x, but inside functions are exactly same. Got it? Understood? Or do you have any questions on this? So this is how actually, this is just an understanding how we are writing these equations. So ideally, if you know this methodology of writing the complementary function equal roots like this, and then if these are non-equal roots, then actually this is going to be a1, this is going to be a2, but this x won't be there. If the roots are real and equal, then this is exactly same as this one, but these functions are arbitrary functions are different, but one function has to be multiplied with x. Suppose if there are two different equal roots, then one with x, another with x square, another arbitrary constant is going to come in. So this is exactly the same methodology what we have adopted in case of ordinary differential equations. There is no difference between ODE and PDE in this particular case of homogeneous equations. Clear? Got it? So this is just, I proved it. Now actually in the next class, I am going to deal with the help of these homogeneous differential equations, how we are writing the complementary function for different cases, and also the particular integrals. So that solves the homogeneous linear equations for us. Do you have any questions on this? Any questions? Okay, yeah, so that's all for today. Thank you. Good night. Yeah, roots may be imaginary also. That case actually. So I'll just see I'll just see if that is present in our syllabus. If it is yes, then I'm going to discuss that as well. So in that case, right, if the roots are imaginary, in that case actually you are going to get the solution as the functions of sine and cosine, exactly the way we did in case of the ordinary differential equations. So here also it will be sine and cosine which you are going to get it. So but actually let me check if it is available, if it is there in the syllabus, then I will discuss. Got it?